Welcome back. Now we're starting the third lecture by Ramadevi.
Okay, so I kind of told you in the last lecture, you have a partition function which is explicitly metric independent, so it captures the topological features. The z of m, which is the partition function, is proportional to the three-manifold invariant or the WRT invariant. And this, along with this, if I want to look at observables, which is metric independent and gauge invariant, those expectation values are also topological invariant, which will capture the information about the knot, for example, the trefoil, and these are supposed to be the knot invariants, where I placed the fundamental representation of SU2 on those Wilson lines, or on the trefoil I put the fundamental representation of SU2. Okay, and interestingly, Witten in 1988-89, he showed that this object expectation value of a trefoil, and you can concentrate on one particular crossing, change it to undercrossing, concentrate on that crossing, make it into no crossing. It satisfies exactly the same recursion relation which Jones had introduced. So that was an important work which led to a lot of activities. Okay, so I will give you what are the ingredients which went into getting the recursion relation, and then you see that from physics point of view we get a interpretation for the skin relation. And in the skin relation, Q was arbitrary, right? The polynomial variable Q here was arbitrary. In this work, Q will be related to the coupling constant, and so it is actually a root of unity with K, which was the coupling constant in my Chern-Simons action. So there is some kind of a formal way in which you can relate the variable Q. There it was some arbitrary value, but here Q will have a meaning in terms of K, and this 2 is because of SU2. If you did SUN, you will have a K plus N. Okay. And there is also a variant of Jones polynomial by 6 and another 2 independent people. Home fly PT is what we call. Okay. So they had come with a 2 variable generalization, which will be, I think, A inverse, and Q par half minus Q par minus half, where this A variable is related to the same Q, but this one will be K plus N, and then it is Q to the power of N. Okay, so these are the if you do SUN. Okay, and we will confine to SU2, which is N equal to 2. But he reproduced even for SUN with fundamental representation, that you get the home fly PT polynomial. Okay. So what are the ingredients? One, of course, is every knot you try to draw it as a closure of a braid or quasi-plait of a braid, which I have already explained in the last lecture. So 2 ingredients. One is closure of braid or quasi-plait It's great. Second is you slice the S3 into 2 3 balls. Okay, this is an S2. So what I do is I try to equivalently draw this as a gluing of upper 3 ball with the lower 3 ball, where this upper 3 ball has S2 and this one will be oppositely oriented S2, so that you can, suppose you put some kind of a current, then this should be in the opposite direction, so that you know when you glue it back, this piece is gone and you end up getting the S3. Now you can start putting knots here. We can put disconnected pieces of knots here. Okay, and you can splice anywhere. It is not that you have to splice this way. I could have put a splicing in such a way that the K2 is here. Okay, fine. We want to prove a couple of things. We want to say that expectation value of K1, K2, what do we want to show? This is one we need to show. Correct? The second thing is, we just want to use this property that you can splice. You can have knots where it could also be lying, let's say, I splice it here where it is A and B. Okay? I can do this kind of a splicing. So what will this be? It will be an upper ball with A, and you can have a lower ball with oppositely oriented S2 boundary, right, and with B. Fine. Here I would like to look at Wilson loop operator for a connected sum of A with B. Right? And what do I want to show? I would like to show this as Wilson loop operator of A right? Everything is fundamental because those properties I want to obey. Correct? Connected sum should be connected sum of the invariants divided by a naught, and if it is disjoint pieces, then that invariant should be product of disjoint pieces. Okay, and then this continues. It continues further to say that I would like to look at it as a we can go to drawing the simplest trefoil. Right, it has 4 punctures. Okay, so So this will be like, if I glue this, I should be able to get the okay. So every knot in S3, I should be able to see it as gluing of 2 3 balls with oppositely oriented S2 boundaries. This doesn't have any puncture. This has 2 punctures. This has 4 punctures, and we can continue. You can keep drawing where you can put, but it will always be how many punctures? It will always be even number. Why? If there are some things going in the knot, some things have to come out. So there should always be a equal number of, right? Okay. So this is something which you will see, that the punctures will always be even number of punctures, at least in these contexts. Okay. So if you put it with across one puncture, some kind of a slicing, then you will get some meaningless answers. So you need to make sure that things are the net. If you put charges, the net charge here should be opposite to this net charge here, so that and 0 also. Some strands, if they go up, some strands have to come up. This is what you see. If you take parallelly oriented strands here, you will see that 2 of them are ingoing and 2 of them are outgoing. Okay, same thing here. Okay. So as far as this ball is concerned, if this was going into the ball, this one is outgoing from the ball. Okay, so you have to keep track of them when you are doing those calculations. So many times what we do is, if we put a representation R here, we're not looking at only fundamental. If it is ingoing, we put R. If it is outgoing, we put R bar. Okay? This is the way we will try and say. But for the oppositely oriented boundary, it's the opposite. This R will look like R bar, and R and R. Okay? If you put any other representation of SUN group. So the second ingredient was that to evaluate any knot in S3, any of these knots, we try and associate a state psi on the S2 boundary, and this one will be in the dual space. Let's say that the state is some phi. Okay, so this will have information about K1, this will have information about K2. Okay. This is the claim. Witten's proposal is that a Chern-Simons invariant inside S3 can be viewed as taking an inner product of these 2 states. Then you can ask a question. The state belongs to which vector space? Okay. So this is where this state is element of space of correlators in a 2-dimensional conformal field theory, which is with current algebra symmetry. So if you are doing SU2, then you have a current algebra symmetry or an affine Lie algebra, which is SU2K. Okay, on S2 with n punctures. Okay. So here the puncture is 0, puncture is 2, puncture is 4. Depending on that, you can define the dimensionality of that vector space. Okay. So the dimensionality of this vector space with no puncture S2 is one dimension, trivial. This has a trivial representation. So if it is one dimensional, you can try and show that this should be proportional to every other. You can insert a state which is one dimensional and you can show that this property will be satisfied. Dimension of the Hilbert space with two punctures. Let's say puncture carries one representation R1, puncture carries another representation R2. This will also be one dimensional provided R1 and R2 are conjugates of each other. This is what is seen explicitly, that one is ingoing, the other one is outgoing. Right? I said R and R bar. So this will again be one dimensional only if it is this. If it is not the case, then it is going to be 0. And dimension of this Hilbert space with S2 with 4 punctures. Okay. So again you can work this out. You will see that this will be, if I take this to be R cross R as I1 to S Ei, if I take the tensor product of two representations, if the number of irreducible representations decides for you this one. For example, if I had fundamental, this will give you this and this, which means it is S is equal to 2. Okay. So you can show that it is 2-dimensional for SU2 fundamental representation. You can work it out if you, it's not even 2-dimensional for SU2 fundamental. Even if you take SU and fundamental, it is still 2-dimensional. Okay. So the dimension of the Hilbert space of S2 for 4 punctured is going to be 2-dimensional if R is this and group is SU1. Okay. Fine. Yeah. So let me work it out for this case using that it is dimension is 1 dimension, and I'll give you a way to do when it is 2 dimension to derive for you the skin relation. Okay. So for 2 punctured S2 boundary, let us insert an identity operator. So 2 punctured S2 boundary, you know the dimension of the Hilbert space is 1 if R2 bar, right? So let me introduce this formally as if I look at S3 with So this is like formally when we write in a one-dimensional vector space, we write this as this with psi, where psi is one-dimensional. This is giving you an identity operator. Pictorially, I would like to look at this identity operator. This is the outer product, which I have drawn it this way, and this is the inner product. Is this clear? I just take the inner product of this and this, will give you this. Okay, so if I use this as an identity operator here, okay, what do I get? To use the identity operator, then we get V of fundamental of A, right? And then V of fundamental of B divided by, this is nothing but and a knot. Okay. So using just the dimensionality property and trying to pictorially give a state, because it's one dimensional, I can write the the single state as an identity operator, as an outer product of these two states. And you plug it in here in the unit operator here. So the top piece will go along with this state, which is this. That will give you this expectation value and expectation value. So what have we shown? I have shown that this is nothing but right. I have shown for you that using the property of the second ingredient, I can directly show that the connected sum respects the property of the skin relation. Can I get the skin relation is the next question. And we go to the skin relation here. What does this tell me? The dimension of the Hilbert space is two-dimensional for fundamental representation. So you can write three states, psi 1, psi 2 and psi 3, such that A psi 1 plus B psi 2 plus C psi 3 has to be 0, because it's two-dimensional vector space. One of them will be linearly dependent on the other two. So you can choose a linear combination of three states to be equal to 0. Fine. And how do I pictorially depict psi 1, psi 2, psi 3? I do the pictorial depiction of this. Start psi 1 to be a 3 ball. Overcrossing. Psi 2 to be a 3 ball with no crossing, and psi 3 to be a 3 ball did I draw the same line? Yeah, under crossing. Okay, right there. So you can plug this in and write A of this in a combination of this is. And what you can do on top of this is that you can have a psi state, which you could take it to be the oppositely oriented we can put that in, and what will end up here, if I put an oppositely oriented side, what do you get? You get some trefoil here, because this will give you a trefoil, I think. Did I make a mistake? Yeah, it's the other way around maybe. Or this one will give you a trefoil, one of them. Okay. Fine. And this one will be with no crossing, and this one will be without. Now the question you can ask is, he has to find A, B and C. Should be exactly like the one which was there in Jones' result. And to find that, what you can do is B psi 2 can be written as some B operator on psi 1. Okay, you can put an appropriate orientation so that it is, the braiding is going to unwind that, and then you can write this as B squared on psi 1, right? Okay. So what does this tell you? It gives you a characteristic equation as B squared, right, minus Y times B plus some C equal to 0 on the braiding operator. This is also, the braiding operator is also defined on the matrix representation should be on a two-dimensional vector space, and it should satisfy this characteristic. So what are these Y's and C's will be? If I know the eigenvalues of these matrices, Y will be the sum of the eigenvalues, right? It's like a root of a characteristic equation, and this one will be a product of eigenvalues. Clear? Is this clear? So Y will be lambda 1 plus lambda 2, and C will be lambda 1 lambda 2. Okay. So this, if you know, in this conformal field theory which I was saying, these are known. There are two different kinds of braiding eigenvalues. Since in the morning there was this issue about frame knots, let me try and say that, and then you will see the skin relation appear. So there are two different braiding eigenvalues. Okay. One for ambient isotopy is this thing, we call it as a standard framing. And second is regular isotopy, which we will call it as framed not invariance. This is, we call this as vertical framing or blackboard framing. Okay. So the ambient isotopy invariants are what we need for the Jones polynomial to be checked, and this is required when we start doing surgery of frame knots. We need this, and the eigenvalues have to be corrected so that it can be used for ambient isotopy invariance, what we call it a standard framing, and here we take it as a blackboard framing. Okay, so there are two different framings, and these eigenvalues, when I substitute, I have to substitute the one in the standard framing. Only then I can compare it with the Jones recursion relation. Okay, so let me write it. So let me call it as there are two eigenvalues, lambda 1 and lambda 2. Lambda 1, let me, that 1 corresponds to E1 and E2. E1 is the horizontal box and E2 is the vertical box. And this will be up to a sign. You will have this to be so these are the two eigenvalues. I'll leave it you to put these numbers where C of a single box is 3 by 4. Technically, when you have so many number of boxes for SU2, you can write, if there are n boxes, then the C of n boxes is n by 2 into n by 2 plus 1. So if you put n to be 1, you will get 3 by 4. And C of double box will be 1. 2 by 2 into 2 by 2 plus 1 is 2, right? Is that right? So substitute that and you will get lambda of this to be and lambda of horizontal box to be minus, and this vertical 2 box can be shown to be 0. Okay, so I didn't write for the, so this is a singlet or a trivial representation. The Casimir will be 0, so this will give you q to the 3 by 2 with the negatives. Okay, so plug these things in, remove the overall scaling factor, sum of the eigenvalues, product of the eigenvalues, and then you will end up getting the skein relation, which is what Jones wrote for fundamental representation. Okay, so this is in Witten's paper. It is not that I am saying it with this frame correction. So if I want vertical framing, I will just put this to be 1. Okay, or the standard framing is where I need to put in this frame correction because I need the ambient isotope. Is this clear? So substitute it here, the lambda 1 plus lambda 2 and lambda 1 lambda 2, and compare this equation with this equation, and you will get the skein relation which relates the trefoil to Hoflink and the knot. Okay, so he reproduced the Chern-Simons way of reproducing Jones polynomial recursion relation, and he has given a 3D definition from a topological field theory point of view. So that's why it was very, that was one of the work which was around the time I joined for my graduate studies, and I found this to be very exciting. But what was bothering us was it is all dependent on the skein relation. If you know the polynomials for low number of crossings, then you can find one higher crossing using the skein. Right? So I need trefoil, I need to know the information about Hoflink and unknot. Similarly, you have to keep going. So we wanted to do something where we can directly get the result. So direct computation of getting the result, where you don't need to go through skin relation, and it's more powerful. Once I know the direct computation, I can start doing beyond fundamental. You know, this is fundamental is what I was trying to say, putting on the trefoil and other knots. Start putting spin 1, spin 3 by 2. Change the group from SU2 to SUN. Then it's 2 variable polynomial. Now I have zoo of invariants where I don't need to worry about skin relation. I can directly compute them. So the direct computation is what makes this really powerful. Okay. How much time I have? Another 15 minutes or?
We would rather aim at ending in like
3.
Yeah, like 2-3 minutes. But if you need, we can.
No. I just want to know.
But you have a lot of time in the next lecture.
I agree. Tomorrow I can continue, but
yeah, just to close the thought.
Yeah, fine. So let me just summarize what I said in this lecture. I have tried to give you a feel of so Chern-Simons theory, SU2 with fundamental placed or knots, you will get the invariant. So we'll get the ambient in isotopy invariance, right, for all knots. They are going to be the same as Jones for the knot up to an unknot normalization. So if you write Jones here, you should put the unknot here, or I will put the unknot here. Okay. Someone was asking, if I do a link, will it be unknot square? No. Whether you do link or not, the normalization which matches with the Jones is with the unknot. Okay. So this is, and the result was skin relation was obtained, was reproduced for this. Okay. This was done by Witten. Okay. And the variable Q is 2 pi I by k plus 2. It's just one variable polynomial. The same thing I could have done for SUN fundamental, and then what you get is unknot SUN. Okay, what you get here is the home flight. Okay, so all of these are validated with the two variables a equal to q to the n and q is e to the 2 pi I by. Okay, so let me stop here. So tomorrow what I will do is I will do the direct evaluation for a 4 punctured boundary, and then I will also show you direct evaluation. Even if you increase the number of boundaries, I will give you at least a flavor of how that is done. And then 3-manifold invariants. Okay, so the next 2 lectures I will try to confine to those 2. Yeah, let me stop here. Yeah.
Questions?
Can you say this for connected sums, like many connected sums, the normalization? Like if I take k1, k2,
Connected sum also is the same thing.
just one unknot normalization. normalization.
Yeah, first you write the connected sum in terms of the products of the pieces divided by a naught. That is going to be there. On top of it, there will be a non-naught divided. That's it.
So there's two.
That comes because of a consequence. The connected sum invariant is this piece is correct, right? Connected sum. This invariant has nothing to do with normalization. If I ask you what is the invariant for this invariant will turn out to be this is true always. Even in Jones it is true. It's nothing to do with in Jones he would have written q power half plus q power minus half. He won't say it as unnaught. If he says the unnaught is 1. In Jones, he would have written this as I showed that also in the recursion relation. This is true whether I do Jones or normal or the Chern-Simons invariant. After that, I want to write my, this is an invariant which I say I'm Chern-Simons theory. If I want to match it with Jones, I have to take this and divide it by the unknaught to compare it with that.
Will you show the same for links tomorrow?
Connected, it's nothing to do with links or knots. Whatever I am saying here, this piece could have been a link also.
Yeah, I mean multicolored. For links you'll show tomorrow.
Multicolored, yeah, different representations. I will mention it in the. Let me first do the direct evaluation for this simple. But whatever I have said here, it's not only this. If I put both the representations on the two component link as fundamental, this is also true. Then when I do it, it's only unknaught which you have to normalize. This is true, but same colors. Jones polynomial will match only if you put same colors. Same fundamental. You can, in principle, in Chern-Simons theory, I can put different colors in different components. That I will modify how the eigenvalue should change. Okay? Yeah. Yeah.
So if I try to do this computation from a physical perspective, so with Feynman diagrams, I have to introduce later. In principle, this should spoil like metric independence, but in the end, it's not the case. There is some framing anomaly, if I remember correctly.
Yeah. So there is a framing ambiguity anyway, but you know how it will change under framing. That you know, and you are going to fix a specific framing and do the calculation in that framing.
So here you fix the framing.
Standard
You
framing.
have already fixed the framing.
That framing is the correction here.
Okay, these are okay.
Yeah. Otherwise, you cannot match. Okay, when you do one twist, the frame changes. You frame correct it. If you do double twist, you have to change the frame by twice. So that's why the lambda 1, lambda 2 eigenvalues. When you take the product, it will take care of that framing done twice, so that skin relation will be reproduced because of that.
Okay.
Yeah. It is framing is dependent, but you can fix the framing and you can get the results in what frame you want. That's what I'm saying.
Okay.
Okay, so let's thank Ram again for the whole day. And we will meet again in 10 minutes, quarter past, to listen to a seminar-style talk by Fabot. Stop recording.